Hi everybody, welcome back. This is our final video for Chapter 5 in AP Chemistry, and really we just have to talk about theory today. So the first theory you have to know is the kinetic molecular theory, which is basically a theory that describes how gases should behave. I say should because this is the theory that describes the behavior of an ideal gas. Ideal gases behave ideally when the pressure on them is low and when the temperature is high, and when the attractions between them are low. But obviously when those conditions vary, so does the gas behavior. So this is ideally how a gas should behave. Okay? First of all, we assume the volume of a gas particle to be negligible, which means that gases take the volume of their container. And that's why when Bryce asked in class today about the, I forget what the volume was, 0.650 liters, why we could use that for oxygen and for water vapor or whatever. Because it doesn't matter how many gases are in there, if the volume's 0.65 liters, each gas will occupy that whole space. They'll spread out and diffuse and intermingle to occupy that whole volume. So whatever the volume is of the container, that will also be the volume of the gas, no matter how many gases are in there. You don't have to, like, if there's two gases, cut it in half or anything. They spread out and occupy the whole space. As we know, gas particles are in constant motion. Think of them like pinballs in a pinball machine. The gas particles collide with each other, and they collide with the walls of their container. When they collide with the walls of their container, they exert pressure, and that is what we know as vapor pressure. Ooh, look at that color. Super, like neon green.
Ooh.
When the gas particles do hit each other, they do not attract, nor do they repel each other. They hit and bounce off, hit and bounce off, hit and bounce off, and we call those elastic collisions. And we do know that kinetic energy is directly related to temperature in Kelvin. So there's a direct relationship between the average kinetic energy, which is the motions of the molecules, and the Kelvin temperature. We have an equation that we've already learned to calculate the average kinetic energy. So the average kinetic energy of a sample of gas is really dependent on one thing, which is, temperature. Okay, just solely dependent on temperature. Okay, so I think there's something here, but it's probably not going to show up. You have it on your table. Conditions that cause a behavior to act ideally. So ideal gases are most likely light, like hydrogen and helium. And they're most likely nonpolar, so they have no forces of attraction between them, or weak forces of attraction between them. And they need to be at conditions of high temp and low pressure. When you deviate from these conditions, we no longer call you an ideal gas, we call you a real gas. And the gases that are most likely to deviate from this behavior are those that are polar, because they'll start to attract each other, right? Polar molecules have partial charges, and so they'll begin to attract each other. And if you smush the gas, so if you have high pressure and low temperature, a gas will deviate from ideal behavior. But all ideal behavior means is you follow those rules that we just listed on the last page. Okay, what we want to be able to explain is the relationships that we've already learned about pressure and volume, and how the KMT can explain it, how we can use the kinetic molecular theory to explain it. So we know that when we're at a constant temperature If the volume's decreased, the pressure's increased. This makes sense, okay? If I have 20 students in this school or in my classroom and I let just them pretend they're gas molecules, I let them walk around, right? And they're going to collide with the walls of their container. But now if I decrease their volume, and I put them in the back room, all 20 of those students, there's a greater chance of collisions with the walls of their container. So since they will hit the walls of their container more frequently, they will exert more pressure. So let me write that down and then we'll come back. So the KMT is able to account for this because in a smaller volume, the molecules will hit the walls of their container more often, exerting more pressure. So given the same temperature, the greater the smaller the volume, the greater the pressure. You squeeze those molecules into a smaller space, and that makes completely logical sense. The next one is pressure and temperature, and we can account for the relationship between pressure and temperature very simply. If the volume is constant and you increase the temperature, so imagine you're in a sealed, closed, rigid container, and you increase the temperature, you are going to give the molecules more energy, and they're going to move faster and faster and faster and faster. So not only are they going to hit the walls of their container more often, but they're going to hit the walls of their container harder. Okay? So if we put that into words, when temperature increases, there are more collisions of more energy, if that makes sense, with the walls of the container. Exerting more pressure. Okay? So that one makes logical sense too. We'll get to volume and temperature next, and this one is a little bit harder to understand because you have to think of keeping the pressure constant. So if you increase the temperature, you know you're going to provide the gas molecules more energy. You know they're going to hit the walls of their container more frequently and exert more pressure. The only way to maintain that steady pressure is to give them more space to bounce around in. So that's the idea behind volume and temperature. You have to be at constant pressure. And an increase in temperature means the particles hit the walls harder with more force and more frequently. The only way to keep the pressure constant is to increase the space the molecules have, and that is to increase the volume. Okay, two more, and then I think we have a special message. Okay, so the next one is volume and moles. The ideal gas law predicts that the volume of a gas at constant temperature and pressure directly depends on the moles. This is a no-brainer. You're going to maintain constant temperature and constant pressure. If you put more gas in, you add more moles of gas. The only way to keep the pressure constant is to have more space. So the more moles is a greater pressure. So increasing pressure, increasing moles would result in increasing pressure. The only way to keep pressure constant is to increase volume. Okay. And then finally, Dalton's law of partial pressures is the idea that the ideal gas law states that gas particles move independent of one another, move and act independent of one another. So what that means is the pressure a gas exerts by itself is the same as the pressure that same gas exerts in a mixture. The identity of the particles is really insignificant, okay? So really, again, today was all about theory. We just had to explain how the kinetic molecular theory and what we know about gas behavior can account for the relationships that we've already learned. I think we have a special message, so let me pause the video, and then when we come back, we'll play that special message.
All right, hey guys. I know for a lot of you guys, this is Christmas time, and it's very special. But there's one person in our class who...
Max.
Yeah, Max, well, Coleridge, who... He can't...
He doesn't celebrate.
Yeah, Christmas. He is Jewish.
So please wish him a happy Hanukkah.
You know, that would be a polite thing to do. I felt like since he's my buddy, we should help him out. There's not many people in the school are Jewish.
We made him the Star of David and put it on top of the chemistry.
We felt like that'd be right. So, all right, guys. So tomorrow, just wish him happy Hanukkah because this is a big time for him. He only gets one present though because he's a poor Jew. But all righty. So.
Thank you, everybody.
All right. Thank you, everybody, and have a great night.